Welcome to the deep dive. Today we're looking at something really interesting, making these already powerful AI large language models even more capable.
Yeah, LLMs are incredible at language, but they do have this, well, inherent boundary.
Exactly. Think about it. An LLM knows a ton from its training data, but it's kind of frozen in time, right? It can't just, you know, check today's news or book a flight for you on its own.
That's the core limitation. They're amazing with the info they have, but accessing real-time stuff or interacting with the outside world, that needs something extra.
Right. And that something extra is where it gets cool, giving LLMs tools. We're talking about connecting them to things like web search, databases, maybe even a calculator, basically letting them outside their own brain.
People might hear terms like zero-shot tool use or maybe function calling. It all boils down to giving the AI ways to use external capabilities, usually through APIs.
And this isn't just theory. The big AI platforms, GPT-4, Claude, they already have things like plug-in APIs, structured function calls built in.
Which really shows this is the direction things are heading, making these models less isolated, more interactive with other services.
Okay, so more tools, more power, sounds great. But as the number of these tools, these APIs explodes, it turns out it's not quite that simple. New problems are popping up.
Yeah, just throwing like hundreds of tools at an LLM doesn't automatically make it better. In fact, it can make things worse.
How so? What kind of problems?
Well, there are two main issues emerging: prompt bloat
Mm-hmm.
and what you could call decision complexity or decision overhead.
Okay, prompt bloat. Let's break that down. You mean the instructions you give the model get too long?
Exactly. You have to describe every single tool, what it does, how to use it in the prompt you send to the LLM. That prompt gets huge.
And LLMs have limits on how much text they can process at once, the context window. So you run out of space.
You're out of space, yeah. But it's also that stuffing the prompt full of tool descriptions can just confuse the model, especially when lots of tools do similar things.
Ah, okay. So if you have like 5 different weather APIs, how does it pick the right one if they all sound kind of the same in the description?
Precisely. It gets harder for the LLM to distinguish the subtle differences and choose the best tool for the specific task.
And that leads to the second problem, the decision overhead.
Right. Faced with this massive list, maybe hundreds of options, the model struggles. It might even hallucinate an API call that doesn't exist or just pick the wrong tool entirely.
We've actually seen this happen, even with the really advanced models.
Oh yeah, the research shows examples where models like GPT-4 and Claude made mistakes when they had too many API choices thrown at them. It's a real challenge.
So just adding more tools isn't the answer if the model can't actually use them effectively.
It highlights that we need a smarter way to manage these tools. It's not just about capacity. It's about clarity and focus for the model.
Okay, so this brings us to something called the Model Context Protocol, or MCP. What's the idea there? A standard way for tools to talk to LLMs.
Kind of, yeah. It's proposed as a universal standard, like a common language, for connecting LLMs to all sorts of external data and services.
So potentially an LLM could tap into, I don't know, Google Drive, Slack, GitHub, databases, maps, tons of stuff, all through MCP.
That's the vision. Imagine an assistant AI that can genuinely use all your digital tools. But again, if you have potentially thousands of MCP tools.
You're right back to the prompt bloat and decision problems.
Exactly, which sets the stage perfectly for the main thing we want to dive into today, RAG-MCP.
RAG-MCP, retrieval augmented generation for MCP. Okay, so what's the core strategy here? How does it try to fix those problems?
The core idea is actually pretty elegant. Instead of giving the LLM descriptions of all the tools at once, RAG-MCP dynamically fetches only the descriptions of the tools that seem most relevant to what the user just asked for.
Okay, like retrieval augmented generation for answering questions, where instead of the whole internet, it just looks up relevant articles.
Perfect analogy. Same principle, but applied to actionable knowledge about tools, not just static facts. It retrieves tool info on the fly.
So how does it know which tools are relevant?
Well, all the tool descriptions, their MCP schemas, usage examples, everything, they're stored externally, kind of like in a separate library or memory.
Okay.
And this library is indexed semantically, meaning tools are organized based on what they do, their meaning. Similar tools are linked together.
Right. So when I ask the LLM, say, what's the weather in London? What happens in the RAG-MCP system?
A dedicated retriever component, basically, a specialized search function, looks at your query, weather in London. It then searches that external tool library and finds, say, the top 3 or top 5 tools whose descriptions are semantically closest to your request. probably weather APIs in this case.
And only those few descriptions get sent to the LLM.
Exactly. Only the descriptions of those top kit candidates are actually put into the prompt for the LLM.
Ah, I see. So instead of a massive list of hundreds of tools, the LLM gets a short, focused list of maybe just a handful of highly relevant options
Precisely. It dramatically cuts down the prompt size.
and makes the decision process way simpler for the model, presumably.
That's the goal. Less noise, less confusion, easier choice. Plus, adding new tools is easier too.
How so?
You just add the new tool's description to that external library and index it. You don't have to retrain the main LLM, which is a huge advantage.
Okay, let's break down RAG-MCP a bit. You mentioned the retriever. Is it just doing keyword search?
It's usually more sophisticated. Typically, it uses vector space semantic search. It converts the user's query and all the tool descriptions into numerical representations vectors. Then it finds the tool vectors that are mathematically closest, meaning most similar in meaning, to the query vector.
Got it. Semantic similarity, not just keyword matching. And you mentioned an optional validation step.
Yeah, that's a neat addition. Before actually using a retrieve tool, the system can optionally generate a quick test query based on the tool's description.
Like a pre-flight check.
Sort of, yeah. It tests if the tool responds roughly as expected. It helps catch basic compatibility issues before handing it off to the main LLM.
Smart. So retrieve relevant tools, maybe validate the best one, and then what's the final step? Invocation.
Right. Then, only the description of the single best retrieved and potentially validated tool is actually given to the LLM.
Just one.
Often just the top one, yeah. The LLM then uses that focused description to plan how to call the tool, figure out the parameters, and execute the user's request. Much simpler than juggling hundreds.
Okay, this R approach sounds really promising. To see how promising, let's go back to that prompt bloat problem. You mentioned an MCP stress test.
Yes, the researchers designed this test specifically to measure how badly tool selection degrades as you just keep adding more and more tools to the prompt.
How did they set it up?
They gave the LLM N different tool descriptions, MCP schemas.
Nah.
Only one of those N tools was the correct one for a simple web search task. The other N-1 were just distractors, irrelevant tools.
Okay.
And they varied N, the total number of tools, starting from just one all the way up to 11,100 tools presented in the prompt at once.
Wow. 11,000 tool descriptions in one prompt. That's a lot.
It's extreme, definitely designed to push the limits. And the key thing they measured was, could the LLM still find that one correct web search tool amongst all the distractors?
And the result? Did it manage?
As you might guess, performance dropped off significantly as N increased. The more distractors, the harder it was for the model to find the needle in the haystack.
Which really proves the point about prompt bloat and decision overhead being serious issues.
Absolutely. It quantitatively shows the degradation.
So then they tested RAG-MCP against this backdrop. How did it do in comparison?
Right. They set up experiments using web search tasks from a benchmark called MCP Bench. They compared RAG-MCP against two main baselines.
Okay, what were the baselines?
First was blank conditioning. That's the worst case scenario, just dumping all the tool descriptions into the prompt.
The stress test scenario, basically.
Pretty much. The second was actual match, which did some basic keyword filtering first, a slightly smarter baseline, but still relatively simple.
And then RAG-MCP with its semantic retrieval. And they measured accuracy, prompt size.
Yep. Accuracy of picking the right tool, average prompt tokens, size, and average completion tokens, how much the model generated.
Okay, the moment of truth. How did RAG-MCP stack up?
The results were pretty clear. RAG-MCP achieved a tool selection accuracy of 43.13%.
Okay, how does that compare?
Well, blank conditioning, just throwing everything in, only got 13.62% accuracy, and the keyword filtering actual match baseline was only slightly better at 18.2%.
Wow, so RAG-MCP was way more accurate, more than double the accuracy of the next best approach.
A really significant improvement, yes. It strongly suggests that dynamically retrieving the right information is much better than giving it all the information, or even just roughly filtered information.
And did it achieve that accuracy while also reducing the prompt size as intended?
Oh, absolutely. The average prompt size for RAG-MCP was just 10,084 tokens. Compare that to the blank conditioning baseline, which averaged over 2,100 tokens.
So less than half the prompt size, but more than 3 times the accuracy. That's impressive efficiency.
It really is. Interestingly, RAG-MCP used slightly more tokens in its output, its completion.
What might that mean?
It could suggest that because the model had a clearer, more focused input prompt, it was able to engage in more thorough reasoning or planning in its response, which might contribute to the higher accuracy.
That makes sense. Better input leads to better, perhaps more detailed output. Now, there was also that figure 3, looking closely at the stress test results.
Right. Figure 3 visualizes the success, yellow, versus failure, purple, for picking the correct tool depending on its position in that massive list of up to 11,100 tools.
And what did that show? Was it harder if the correct tool was buried deep in the list?
Generally, yes. High success when the correct tool was one of the first few options. Then it got more variable in the middle range, likely because of semantic overlap, tools sounding similar. And then, yeah, performance really degraded. When dealing with thousands of tools, failures became much more common.
So even for the standard model, finding a needle in a really big haystack is hard.
Very hard. Although, interestingly, there were still occasional islands of success, even way out in the thousands. Some tool descriptions might just be uniquely distinctive.
But the overall trend confirms the problem RAG-MCP is solving.
Definitely. It shows RAG-MCP's strength, especially in avoiding those mid to large-scale confusion zones, but also hints that scaling to, say, millions of tools might require even more advanced retrieval.
Okay, so let's boil it down. Why does RAG-MCP work so much better?
Well, three main things, really. First, the focus context filtering. It just removes the noise, removes the distraction of irrelevant tools.
Clearer focus.
Second, prompt efficiency. Using fewer input tokens frees up the model's cognitive capacity, if you will, to actually think about the task, not just wade through descriptions.
More room for reasoning.
And third, that balanced generation. Maybe because of the better input, it seems to lead to more thorough reasoning in the output, which ties back to the higher accuracy.
And thinking longer term, how does this approach handle things just constantly changing, new tools appearing all the time?
That's one of its biggest strengths: scalability and extensibility. Since the tool descriptions live in that external indexed memory, you just add new tools by indexing them there. No need to retrain the giant LLM every time a new API comes online.
Which is huge, practically speaking.
Massive. And also, because it only retrieves and considers the relevant tools for a given query, it only needs to potentially activate the servers for those specific tools on demand.
Ah, so you don't need potentially thousands of services running constantly just in case the LLM needs one?
Exactly. It avoids a potential infrastructure nightmare compared to systems that might need all registered tools to be constantly active.
So wrapping up the core message here, RAG-MCP looks like a really smart way to let LLMs use this growing universe of tools without getting bogged down.
That's the key takeaway. Selective retrieval beats information overload. It leads to much smaller prompts and significantly better accuracy in using the right tool.
And where does this go next? What's the future research focus?
Well, definitely refining retrieval for even larger tool sets, maybe hierarchical indexes, more adaptive methods, also tackling multi-tool workflows, how to chain tools together effectively using Argy.
Right, because one request might need, say, a search, then a calculation, then maybe sending a message.
Precisely. Coordinating multiple tools is the next big step. And of course, moving this from research into real-world AI agents that can reliably use lots of tools to help us with complex tasks.
It's really fascinating. So maybe something for you, the listener, to think about. If AI can accurately and efficiently tap into this vast web of digital services and tools, what does that actually unlock?
Yeah, what new kinds of applications become possible? How could it change how we interact with technology or solve problems that are currently too complex because they require coordinating too many different systems?
What specific challenges, maybe in your own field or daily life, could suddenly become tractable? Lots of potential there. Thanks for taking this deep dive with us.